In this video, you will learn how to calculate the energy either absorbed or released during a phase change. So we've gone over the fact that temperature does not increase during a phase change. Instead, all the energy that's released or absorbed is used to power the phase change. On the phase change diagram, this portion of the heating curve has a slope of 0. So those parts of the heating curve here are this part here. This would be vaporization if we're thinking about moving from left to right on this chart. And down here is fusion or melting. So today we're going to calculate how much heat is absorbed or released during a phase change. We're going to use water as our example, but a similar calculation can be done for other substances. So you're going to see that mass is part of this calculation, and I think these pictures will kind of show you why. Obviously, a smaller amount of energy is going to be required to melt a small amount of a substance than a really large amount. So the amount of heat absorbed or released during a phase change is generally called the latent heat of transformation. But different substances have different latent heats of transformation, and on top of that, different phase changes absorb or release different amounts of heat. For example, less energy is absorbed to melt ice than is absorbed when water is vaporized. You have a table in your notes that contains the heats of transformation for water. You could also look this up online. So here's our equation. It's heat, this is the heat, and it's going to be measured in joules, equals the mass in grams times the heat of transformation. And the heat of transformation is, oh, there's a typo there, it has an S in it. Transformation goes with the substance, so it's particular to the substance, and the phase change. So you have to have really clear information about what item you're either melting or vaporizing or freezing or condensing. You need to know. So here's our first example. We're going to use water. So water is what we're using in all of these examples as our substance. And then we need to read to see what it's doing. So how much heat is required? Required is going to tell us that we're absorbing heat. To melt, okay, that's fusion. 1,000 grams, that's our mass, of ice at 0 degrees Celsius. The temperature value in here is just to tell us that we're at the melting point. So if we weren't at the melting point, we would have to do an additional temperature change calculation in order to get our ice to the melting point. But because we're there, we can just use the phase change calculation. So mass is 1,000 grams. And our heat of fusion for water is 333.9 joules per gram. And then we just multiply that. And our answer is 333,900 joules. That's the amount of heat that's absorbed. This is a really big number, so we might want to actually convert this to kilojoules. 1 kilojoule equals 1,000 joules. So to convert this to kilojoules, we would just move the decimal point 3 places to the left. So it would be Q equals 333.9 kilojoules. So that's just an option. Here's our next example. How much heat is needed? Again, that's going to indicate absorbed. To vaporize 200 grams of water at 100 degrees Celsius. Okay, vaporize is our key word here. We're going from liquid to gas. We have 200 grams. That's our mass. Again, we're working with water, and we're at 100 degrees Celsius. We know that's the boiling point. So again, we don't have to do an extra temperature change calculations. We're ready to have that vaporization happen. So we just write down our equation, and we start filling it in. Our mass is 200 grams. Our heat of vaporization is 2,256.8 joules per gram. We multiply that, and we get 451,360 joules. And like on the last problem, if we want to, we could convert this to kilojoules just by moving the decimal point 3 places to the left. 1 kilojoule equals 1,000 joules, so this could also be shown as 451 point, we could round it even, 0.4 kilojoules. So either one works. This is sort of the extra step. Here is our next example. How much ice, so again, we're working on water and all of these, at 0 degrees Celsius, so that's at the melting point, can be melted by 100 joules of heat. So this problem is actually giving us Q, and it's asking how much ice. So it's looking for the mass. So we would write down our equation, and then we would fill in what we know. So we know that we get to expend or absorb 100 joules of energy. We're looking for M. We're going to then multiply the heat of fusion here because we're at the melting point. Again, you don't have to memorize these heats of fusion or vaporization. You can look them up. Okay, so we're trying to get mass by itself, or M by itself. So we need to undo this multiplication by dividing. The same thing on both sides of the equal sign. That is just, using the algebra that you know. So that's going to cancel. 100 divided by 333.9. That's going to be a small number because we're dividing 100 divided by something that's bigger than 100. So we know that our answer is going to be less than 1. And specifically, we can punch that into a calculator. We get 0.299 grams. So our answer is 0.299 grams of water, to be specific. And that's how many grams of water could be melted by just using 100 joules of heat. So it's not much water. That's the end of our lesson for today. I hope that was helpful. Have a good afternoon.